Hi everyone, my name is Johannes Engelsberger. Here I'm presenting to you our RSS 2020 paper, MPTC, Modular Passive Tracking Controller for Stack of Tasks-based Control Frameworks. This is a really beautiful control framework, which I recently created with my colleagues listed here. All of us working at the German Aerospace Center DLR. Having an arbitrary robot at hand, may it be free-floating or fixed-base, the basic idea is to assign various impedance-based controller modules, the so-called Modular Passive Tracking Controllers, to different parts of the robot. The corresponding tasks may, for example, be formulated in Cartesian or joint space. Now the different control objectives are combined into a stack of tasks, which is basically a mapping from the optimization variables via the stack of task mapping matrices to the stack of task vectors. Now the stack of tasks is solved via an optimization. So, for example, using a pseudo-inverse or a quadratic program. And the most critical point is that the overall controller synthesis is passive, if possible at all. In contrast to inverse dynamics, MPTC is not only nice in theory, but also in real-world settings. In the following video, we will see our humanoid robot Toro walking based on MPTC. It is quite remarkable that this experiment has been taken just a few hours after trying the controller for the first time on real hardware. Now let's get started with some theory. Here we see the general robot equation of motion. Q dot and Q dot dot are the derivatives of the generalized coordinates Q. M is the inertia matrix, C the Coriolis and centrifugal matrix, tau G are the gravitational torques, and tau are the generalized forces. Next, I'll present some task space considerations. For every task, we define a Lyapunov function Vk, which consists of the relative potential and kinetic task energy. Here, Kk denotes a constant task stiffness, Mk is the task inertia, and Jk is the task Jacobian. X tilde dot k is the task velocity error, and X tilde k is the corresponding task position error. Now we introduce the task force, which maps the generalized forces tau to the task space via the task actuation mapping matrix Tk. This matrix can be interpreted as dynamically consistent pseudo-inverse of Jk transpose. Next, we define the desired task force, which consists of a gravity compensation term, an overall Coriolis and derivative compensation term, an acceleration feed forward, a Coriolis and damping feedback term, and a position feedback. Subtracting the actual task force from the desired one, we get the task force error F tilde k. Now, in light of this task force error, we get a task Lyapunov rate which is purely dissipative if F tilde k is 0. Similarly, the task behavior becomes PD+-like if F tilde k is 0. Now, let's consider the overall system. We stack all desired task forces, actual task forces, and commanded task forces together. Note that it is important for our analysis to distinguish the two. The overall system Lyapunov function is now the sum of all task Lyapunov functions, multiplied by scalar task weights psi k. Differentiating, we find the overall system Lyapunov rate V dot. Here, the term V dot tilde is a function of the stacked task velocity errors, the diagonal matrix of task weighting scalars, and of the task force error. Finally, we find that the actual overall Lyapunov rate can be expanded into three terms. V dot desired being dissipative for sure, V dot tilde real covering effects like unknown perturbations, wrong assumptions, and joint torque offsets, which cannot be influenced. And finally, V dot tilde command, which covers the effects of the trade-off amongst the tasks. This term is of special interest here, and we will use the corresponding force command error in our subsequent analysis. We can use it to define a cost function g that tries to trade off between the task objectives. In this presentation, we focus on the fully activated unconstrained case. Differentiating g by the optimization variable and setting the result to 0 yields the optimal generalized torque command, which is based on the pseudo-inverse of t. We find that using this optimal command, the desired task forces are mapped via a task force trade-off matrix ET to the task force command errors. If we now first consider the non-conflicting case, and if t is square and invertible, ET becomes 0, F tilde command becomes 0, and thus also V dot tilde command becomes 0. This means that the trade-off has no influence on passivity. Next, we consider the conflicting case, for which t is non-invertible, and thus neither ET, nor F tilde command, nor V dot tilde command becomes 0. However, we first consider the regulation case and make a special choice of task optimization weights Wk, as the product of the inverse of the task inertia with the scalar task weights psi k. The overall weighting matrix W is simply the corresponding block diagonal matrix. In this case, ET remains non-zero, same for F tilde command. However, V dot tilde command becomes zero, which means that again, the trade-off has no influence on passivity. Therefore, we call this special choice the passivity varying optimization weight, or short, PWOW. For the conflicting tracking case, an in-depth passivity analysis is missing so far. However, we observe a very robust behavior both in simulation and experiment. Now, I'll be presenting a bit of an overview and some really nice results. MPTC covers the complete range in between inverse dynamics on the one side and PD plus control on the other side, depending on the granularity of the targeted decoupling, or in other words, on the desired modularity of the tasks. Here we see the results of a fixed-base robot simulation, showcasing the regulation case. Note that the overall Lyapunov function V never increases except for discrete events or in case of perturbations. Here we see a fixed-base robot regulation scenario for an overdetermined controller setup. Note that the subtask Lyapunov functions may grow, while the overall Lyapunov function is guaranteed not to grow. Next, to showcase MPTC's ability to control floating-based robots, I present the result of a simulation of Toro walking in OpenHRP. Except in case of perturbations, we observe precise trajectory tracking, both for the center of mass, or here DCM, and for the feet. The results of the walking experiment that we had already seen are shown here. Again, we observe decent trajectory tracking. It is important to point out that MPTC, as compared to inverse dynamics, requires a very low tuning effort when it comes to its real-world application. The overall control framework of Toro, in addition to MPTC-based tasks, also contains an angular momentum regulation task. Here we see the achieved robustness. Another very important criterion for robot controllers is safety. As you can see, using MPTC allows to safely interact with complex robots. Toro is actually quite huggable now. This is the end of my talk. I thank you very much for watching and hope to see you at my poster presentation.